Okay, so we got to here. Is that true?
Yeah.
Okay, and then we plugged in the numbers from 0 to 5, and Gage said, do this, don't go sideways. Is that right?
Yeah.
I like that idea.
And then you were yelling at me what the answers were.
Yeah, 7.
7. No, for 0 it's 1, right?
Yeah.
1, 7,
23,
49.
49, 85,
131. Okay, thank you. Okay, so Payson, all I wanted you to do is just said create a table of second differences for the polynomials. Yep, so the first differences are just 6, 16, okay, 26, I think I got it now, 36, and then 46, and then the second differences are 10, 10, 10, 10. Okay? No, I said don't do B and C. Yeah, because I didn't want Maddie to have to like have Miss Parkin adopt her and just start living over there. So we just cut it right here. Okay. I don't know that I understand what B and C was even asking. Yeah, so we won't worry about that. Okay, will you? Let's see. Just pass them to Mason. So you got to find it in your book. It's going to be in like the middle somewhere. Oh, we bookmarked that one, right?
Yeah.
Okay, so go to where lesson 1 was before, and then it'll be obviously just past that. And then we decided that you guys get to write in these things as we go. Okay, so you can copy this down in there if you want, use that as your notes. All right, so what we're going to work on today is a little bit maybe easier than the other stuff, well, at least the finding the equations for the other stuff. We're going to multiply polynomials together, okay? And we are going to do it in a exciting way. We're going to do it using an area model. And so to start with, I'm going to show how this works with a very basic problem. I'm not feeling pink. You guys notice anything different? It's like, it pops, right? It's like, wow. You notice that?
Wow.
I had a new projector yesterday, and it's like now everything is just more vibrant. It's like I feel like I'm living for the very first time. It's a really exciting day for me. I want you guys to know that. Okay, so I don't know if you guys saw this when you were in elementary school before or not. But one of the things that they would do before to teach you how to do 28 times 27 without doing like the 2 by 2 multiplication thing is they would put it into this area thing. Do you remember this? No? Okay. So the way that this works is if you're going to do 28, you would go 20 and 8, right? And then we're going to multiply that by 27, so then you go 20 and 7. Okay? And then you just multiply all the things and fill in the squares. So this square right here, this box right here, 20 times 20 is 400, so that goes in here. And then if I go 20 times 7, I get 140. And then 20 times 8 goes right here, and that is 160. And then 8 times 7 is in here, and that is 56. Okay, so then the answer is what you get when you add all of those things together. Okay, so 400 plus 160 plus 140 plus 56, and conveniently, since those add up to 300, you get 756. Okay, so that's a way that you can do multiplication without doing the 2 by 2 kind of thing. Okay, so have you guys kind of seen that one? Maybe some of you have, maybe some of you haven't. Right.
Why don't you try to make things so much more difficult than they have to?
Well, in theory, this is easier because, well, I guess I shouldn't say easier. Just different kids attached to different ways, okay? So there's a lot of kids that are just like, teach me the, this would be called the algorithm, and just do the, 6, carry the 5, 14, 19, 6, what does that, carry the 1, 4, 5, and then get it like that. right? So that's how you guys probably mostly do this. But for other kids, this doesn't necessarily make sense, and they can't remember all of the steps. And so this is a way that you can sort of write it out and make it easier. Okay. The same thing is true with what we're going to learn today, the multiplication of polynomials. You can do it this way, and I'll show you that way, but you can do it this way also. And I don't care which way, you just have to find one that works for you. Okay. The coolest thing about this is that it makes division of polynomials way easier. And in all the years that I've taught how to divide polynomials, that is pretty tricky. Okay? All right, so we're going to call that the tabular method. So we're going to use the tabular method right now to multiply x plus 8 times x plus 7. So what do you think I do with that? X and an 8 on the top. It could go down the side if you wanted. It doesn't matter. And then what goes here? X and 7. Okay, so now I just have to fill in the boxes. What goes in the upper left-hand box? X squared.
X squared.
What goes right here?
8x.
8x. And then 7x. And then 56. Okay, so now if I write this all out and it says combine like terms, there's only just that one x squared, so it just lives by itself. How many x's do I have? 15. Total of 15. And then 56. Okay? Which is the same as what's the way that you've learned to do this before?
The foil?
Yeah, the FOIL thing. So you could also do this by going first times first, and that gives you this x squared. Outside times outside is the 7x. Inside times inside is the 8x. And last times last is 56. So it's just sort of a different way to organize that. Okay? We good? All right. So now this is where this is a little bit handy, because this is advanced algebra, right? So multiplying just a 2 by 2, that's child's play. We're going to do things like 3 by 3s. Yeah. And so you can't do the FOIL thing here because there's not enough letters in that word. You have to go x squared times x squared times negative 5x, x squared times 2, 3x times x squared, 3x times, and all the way. Okay, so sometimes that's hard to keep track of. So we are going to do that using the tabular method again. This time when I make my table or my little box or whatever, how many columns do I need? 3. And how many rows? 3. So altogether there will be 9 boxes. Yeah. Okay, and then I'll just start with the top, but like I said, you can do it down the side first and then go to the top and you're going to get the same answer. It doesn't matter to me. Go. Fill in the squares. We all got the same thing. What goes right here?
X
to the fourth, and then this is?
3x, 3x,
And this is?
x squared.
Okay. Then?
Negative 5x cubed.
And then?
Negative 15x squared.
And then?
Negative 5x.
Negative 5x.
Okay, and then this is?
2x squared. 6x 2.
Okay, awesome. All right, now the fun thing about this, I mean, there's so many fun things already, I should say. The additional fun thing about this is that the way this is set up, when you go to combine like terms, does anybody sort of see a pattern about where they all are?
Yeah.
Where are they? On the diagonals, yeah. So if I just think about this in a sort of diagonal kind of way, I'm going to put this, I don't want to paint. I want to go this way, and then like this, and then like this, and then like this, and then like that. Okay, that wasn't very good. So this one only has the x to the fourth. These two combine to make
Negative
2x cubed. These three altogether make
Negative 12x.
negative 12x squared. These give me x, and this is just plain old 2. And so there's my answer right there. Okay, so what you guys got? Okay, so that's an easy way that you can look at it to combine like terms. And when we do division, it's kind of important that you are able to see that because we're going to do this process, but we're going to go backwards. Okay, so life just keeps getting better and better and better. All right, so will you now try on your own this problem right here? When you are done, please check with people at your table to make sure that you have all the same answers. Okay, so this one was a little bit different. Right after I told you there's this fun pattern, what was different about this? Yeah, right, because it's a 2 by 3, right, and so it lines up in a different way. So one way, if you wanted to, that you could handle that and still have things come out to be pretty. And again, there is actually a reason for doing this that we're going to see later. It seems kind of weird right now, but I could go with x squared, 3x, and 1 right here, and then if I go x squared and then go 0x and negative 2 there, then everything still lines up. You know what I'm saying? Okay. So then you go through, and hopefully you guys all got the same thing. X to the 4th, 3x cubed, x squared, and then when you multiply 0 by anything, it's just going to be 0, right? So those are all going to be zeros in the middle, which again, right now you're like, why do we even write them then? But trust me. Negative 2x squared, negative 6x, and negative 2. And then you still get this diagonal idea of being able to combine the like terms. Okay? So hopefully you got the final answer of x to the 4th plus 3x cubed minus x squared minus 6x minus 2. Yep, okay. All right. Okay, so now that we have the basics down, we're going to get a little bit crazy here and see if we can see some patterns, okay? So this one, I'll show you how to start the table. Do you want to go 2 by 5 or 5, but do you want to look like this or like? Yeah, what? Oh, you do? And how do they do it? Oh, so they have the answers already. Okay, awesome. So will you look at the table in your book and use that to combine the terms and plus you come up with a answer for what this first part is. So the first thing we need to know is what is x minus 1 times x to the 4th plus x to the 3rd plus x squared plus x plus 1 equal. Okay, so look at the work that they've done for you already and then tell me what you think it's going to be no matter what the exponents are. Okay? So if you go through and you combine the like terms on the table that they give you, what do you end up with? A lot of them cancel out, right? Because as that negative 1 goes through, it clears out all the ones that the x's made. So when you combine those like terms, what do you end up with as the final answer?
X to the 5th minus 1.
X to the 5th minus 1, right? Right? Okay? So if I go x minus 1 times, and notice it has to be really, really specific, x to the anything plus x to the 1 less plus x to the 1 less plus x to the 1 less all the way down to 1. What is my exponent going to be right here? So for this one I started with x to the 4th and ended up with an x to the 5th. If I started with an x to the 5th, I would end up with a
6.
x to the 6th. If I start with an x to the n, I'm going to end up with a x to the n plus 1. Good. And then all of those things in the middle are going to get cleared out by the negative 1 and the x. And then what is here at the end? Negative 1. Okay? So that's a little pattern. This I would suggest maybe you write in your notes somewhere because I think that's going to come up again. And if you can see it quickly, then it's going to save you some time. So you might see this huge problem and you're like, oh my God, this is going to take me like an hour and a half. I have to go see Miss Parkin again. And then you actually remember and you're like, okay, no, actually this is super simple. So just jot that down so you don't lose track of it. As promised, I told you that I would show you another way to do this. Okay, so you don't always have to be drawing out tables. and then you can just decide which one you like best, okay? So this is the sort of old school algebra way to multiply these things. So what I would do without making the table is I'm just using the distributive property. So I have to distribute this x to all of these 4 terms through here, okay? And then I have to distribute this negative y through all 4 of these terms here. So what is x times x cubed? X to the 4th. Because remember, this is like x to the 1st, so we're adding 1 to each one of the exponents as we go. What's x times x squared y?
X to the 3rd y.
Good. And then?
X squared y
And
squared.
then?
X y cubed.
Okay. Pause there, make sure everyone besides Gage has it. What did you think your name was? Annie?
Andy.
No. Annie, you got it?
Yeah.
Okay. All right, and then I'm going to do the same thing with the negative y. So someone whose name is not Gage. What's negative y times x cubed?
Negative y.
Negative yx cubed, right. But usually we go alphabetical order, okay? So we're going to go negative x cubed y. You don't have to because multiplication works either way, but that's just the normal thing. All right, so someone besides Gage or Annie, what is negative y times x squared y?
Negative x squared y squared.
Good, negative x squared y squared. How about negative y times xy squared, Mason?
I was writing it down.
Okay, what's negative y times xy squared?
Does that affect the 2? Does it make
Yeah,
it
because
negative?
it's the y and the y. Doesn't make it 2. The negative makes the whole thing negative.
Oh,
Okay, and then since this is just a y, this x doesn't change. But then if I have y times y squared, I get
Y cubed.
y cubed, because this is like y to the 1st, and you have to add the exponents. Okay, and then, what's your name, you think?
Me?
Yeah,
Oh, negative y to the 4th.
that's a weird name.
Oh, Katie.
Kate. Negative y to the 4th, okay? So that would be our first step, and then, yeah, what Gage is noticing is, once again, we have a lot of things canceling, right? Okay, so the x cubed and the y cancel with this negative x cubed and y. X squared y squared cancels with negative x squared y squared. And then xy cubed and negative xy cubed cancel as well. So in the end, I'm left with x to the 4th minus y to the 4th. So the question is, how is this similar to the example that we did in the last one?
They can't.
Okay, a lot of them cancel. Okay. What could we let y equal in this problem to make it exactly the same as the one before? 1, because the other one was x minus 1, right? And then these were all just x cubed, x squared, x, and then just 1, okay? So the previous example we did is just a more specific example of this one. So again, if you can sort of recognize this pattern, it might save you some trouble. These two things are being subtracted. The x's are going down by 1 power each time, and then the y's are going up by 1 power each time, and then this magic thing happens in the end, right? Okay. All right, so what about x squared minus y squared times x squared plus y squared? Will you do that on your own, and we're going to do the distributive property here? So try and do it without making a table. Just distribute or FOIL or whatever you want to call it, okay? This one, since it's a 2 by 2, you can just FOIL, right? So first times first is x to the 4th. And then if I do the outside, x squared times y squared is x squared y squared. You can't do anything with them because there's x's and y's. And then conveniently, inside is
Negative
x squared y squared. And then last times last is
Negative y to the 4th.
Negative y to the fourth. Good. And then what a lot of you notice is that these two things in the middle will cancel, and so you're left with x to the fourth minus y to the fourth. Okay? So, can you generalize that? X to the nth minus y to the nth times x to the n plus y to the n. What is that answer going to be? X to the, what do you do with these exponents here?
Multiply with
You
multiply.
add them when you're I know it's confusing because you're multiplying the bases, but you're adding the exponents. So n plus n is, n plus n is,
Plus 1.
n plus n is, n plus n is 2n. If I have an n and then I add another n, I've got two n's. And then all the stuff in the middle is going to cancel, and then I've got y to the n times y to the n. This time, you got it. When I add the n's, you get 2n. Okay? All right, so there's some fun patterns that you can see in here as you're going through this stuff. Okay? All right, so there's some vocabulary. That looks really intimidating, doesn't it? You don't have to write it down. We'll just chat about it. Equivalent polynomial expressions. What does it mean for polynomial expressions to be equivalent? They're the same. Yep, equivalent, the same. Polynomial identity. That's basically the same thing. Coefficient term. Yeah, nobody cares. All right. Any questions about this stuff?
No.
You're good? All right. So your assignment then, should you choose to accept it. So now I have to go back to the front of the book. And I will try to be a better teacher this time than I was on